Hi everybody, so this is a way that we can simplify something called complex fractions using the division rule. And so what's kind of nice about this one, again, is that it's really built on some skills that we should already be familiar with, mainly how to divide fractions. So what you see here in this kind of series of expressions are some pretty messy, pretty hard to look at fractions. So this first one that's asking us to simplify a over b over c is a fraction over a non-fraction, really. But if you recall kind of how fractions work, you can really think of them as undone division. So I could rewrite this as, I'm going to zoom in just a little bit, a over b divided by c. Now, if we kind of take that a step further and say, okay, this is the same thing as AB divided by C, we remember that C written as a fraction is just C over 1, so A over B divided by C over 1, and that's something that we should be able to work with, right? The way that you divide fractions is that you flip the divisor and multiply. So this is the same thing as A over B times 1 over C. We multiply right across top and bottom, and we end up with A over BC. And there we go. So once again, just interpreting this fraction as a division problem, and then dividing the fractions as we normally would. Let's take a look at this one. We've got A over 1 over C. Now, we could absolutely do what we did in the first one, where we write this as a division problem, and that would totally work. But if we think through this one, we can actually make life a lot easier on ourselves. So as I look at this, I say, okay, we're on A over 1 over C. I kind of lost the line there for the fraction. And I look at A over 1 and I say, okay, well, I guess I could do A over 1 divided by C, but I recognize that A over 1, any fraction over 1 is just itself. So I can actually write this as just A over C right off the bat. And that's all we can do with that one. Again, if you did what we did up top in the first example, it would absolutely work. But this is just a kind of a quicker way based on the situation here. All right. So this is another messy one. A over x over b over a plus x. I might recommend, given the complexity of the situation, that we go back to that division rule. So I'm going to rewrite this as a over x divided by b over a plus x. And once again, just because we have this a plus x in the denominator here, we don't really have to worry about it too much. I mean, this is going to be put in parentheses if we do anything with it regarding multiplication. But I am going to think about this as multiplication. So we got a over x times, I'm going to write the reciprocal of this fraction here. And so what I can rewrite this one as is a times the quantity a plus x all over xb. And we're all set there. Hi everybody, so for this lesson, we're looking at finite and infinite sets, membership in a set, and then rearranging equation before graphing. So there's a couple things that you need to be aware of before we look at this set. The definition of finite is bounded or limited, and then the definition of infinite is without limit. So what we're looking at down here, we're looking at some finite sets. So if you look at this example, it says represent the following numbers as being members of set K. So we're trying to make sure that we have all these in set K. And so the way that you do this, it's more of a notation thing than anything else, is that we're going to take K, we're going to put equal, and then we're going to put these little curly brackets here. And then what we're going to do is we're going to put one of each of these numbers within the set. The order doesn't actually matter. We just don't want any repeats. So I'm going to go at 0. So I got my zeros covered. My 1. Got my 1s covered. Looks like we got a 2 here as well. 4, 5, and 7. And then I close my curly brackets. So this is showing that all of these values are members of this set K. Again, I put them in order from least to greatest, but it actually does not matter what order you put them in as long as you do not have repeats. Now, below we have some sets here written just kind of as what we just did. We have A is equal to 0, 1, 3, 5, B 0, 4, 6, 7, and C 1, 2, 3, 5, 7. And so what we're going to do now is that we're going to answer these questions A through C. And what's interesting is that you have this little sign here, this one right here, and you can really read this as is a member of a set. There we go. That's what that means. And so if you cross it out, the way that you'd interpret that is just that it is not a member of a set. So the little E looking bit says is a member of a set. So we're meant to say, given the sets that we have, are the following statements true or false? So I look at this at A, and I would read that as 5 is a member of set A. So I go up to set A, and I see that, yeah, 5 is in that list. So this would be a true statement. For B, 4 is a member of set C. Well, I'm going up to set C, and I'm not seeing 4 on that list. So that would make this a false statement. And now for C, 5 is not a member of set B. Well, I go to set B here. I don't see 5 on the list, so that's actually a true statement that 5 is not a member of set B. So again, mostly a notation bit for this first section here, but important nevertheless. All right, so now we're going to do a bit of graphing to kind of change gears a little bit. And one of the things that we're going to do is kind of change the equation a bit before we graph. Now I put a little piece of graph paper here. I recommend that you have a piece of graph paper as you follow along because eventually we are going to be graphing. Now as we look at this equation, we notice that it is not in the form that we're most familiar with, which is y equals mx plus b. So what we're going to do is we're going to put it in that form, and I'm just going to write that over here, y equals mx plus b. So one of the things that I notice about this form is that y is by itself. And right now in this equation, y is not by itself. So what I'm going to do is I'm going to change this equation so that y is by itself. And so the first thing that I'm going to do, is write 3x so that it actually looks like 3x. Minus 2y equals 4. I'm going to subtract 3x from each side. So I'm kind of moving in the direction of getting y by itself. There we go. And then I'm going to divide each side by -2. Now be careful when you do this because you have to divide the entire side by -2, like so. And remember that you can simplify this by dividing each of the terms on top by -2. So 4 divided by -2 is -2. And -3x divided by -2, well, I could write that as plus 3x over 2. All right, so last thing I'm going to do using the commutative property of addition is I'm going to switch the order of this. And what I have now is something that we were doing a couple lessons ago. I have y equals mx plus b. So our m is going to be 3 over 2. Our b is -2. And now all we have to do is throw this onto a coordinate plane. So here we go. I'm going to have a stab at drawing this using my little stylus here on this piece of graph paper that just feels a little bit too small. Hey, that's not bad. I've come a long way. We're going to assume a scale of 1. If our y-intercept is at -2, that means that there's going to be a point right on the y-axis at -2. I'm going to read this slope as 3 up, 2 to the right. So I'm going to go 1, 2, 3, 1, 2, which is going to leave another point here. What the heck, I'll do one more. 1, 2, 3, 1, 2. So that now we have our 3 points, ideally with a ruler, but here we go. I connect the 3 rather, and there's my line. Again, doing that rewriting is part of the process. All right, I got one more of these for you. Next page. And so here we are again. This time we've got 3y plus x equals negative 9. And so I'm going to try to change this to y equals mx plus b. And the first thing I'm going to do is try to get the y by itself. And how I'm going to do that to start, whoops, equals negative 9, there we go, is I'm going to subtract x from each side. I'm going to divide each side by 3. Negative 9 divided by 3 is negative 3. Negative x divided by 3 is negative x over 3. And now I'm actually going to give myself just a little bit more space here and just move this over here. So now I'm going to, sometimes what I do is that if I'm subtracting something, I'll change it to its addition equivalent. Like so, as in subtracting x over 3 is the same thing as adding negative x over 3. And then I'll switch the order using the commutative property of addition. So I've got negative x over 3 plus negative 3. And hopefully what this makes really clear is that our m value is negative 1/3 x, or I'm sorry, excuse me, it's just negative 1/3. And our b value, or y-intercept, is negative 3. So now I'm going to go to my little graph here and once again make an attempt to draw a super accurate x and y axis. All right. I'm going to recognize that my b value is at negative 3, which means my intercept is at negative 3. So I made my mark, 1, 2, 3. There we go. Assuming a scale of 1. And then we have a negative slope, as in our rise is negative 1 and our run is 3. So we're going to expect a decreasing value here. So my down 1 to the right 3. 1, 2, 3. Put a point there. Down 1 to the right 3. 2, 3. We'll put a point right there. We connect them. And we've got our graph. So after you complete the practice problems, your homework is right down here. You've got the 2 through 30 even and 3 and 17 on problem set 56 in your textbook.